hello. Thank you very much for that very nice introduction. Today I'm going to be presenting my results of my thesis that I wrote as a part of my Master's in Conservation and Restoration of Cultural Heritage at the University of Amsterdam. I did this project in association with the Rijksmuseum and their project, Japanese Prints: A Closer Look. In addition, I also worked with the Cultural Heritage Agency of the Netherlands and the European Synchrotron Radiation Facility for portions of this research. So a very quick summary of what I'm going to be talking about today. First, I'm going to go into the historical context of what exactly are Edo-era Japanese prints, and then I'll talk a little bit about red lead, how it discolors, and then what I actually did, the analysis I conducted, the reconstruction that I went into, and the results of everything. So, it has been observed that red lead on Edo-era Japanese prints discolors over time. You can see in this print over here that how this red has slowly shifted to black. I chose this research on this topic because understanding the discoloration of these prints further can inform us which prints are at a higher risk of discoloration, tell us about the quality of artist materials being used in these prints, and help me determine if the reconstruction method that I used is representative of Japanese prints from this time, and tell us about a potential intentional discoloration that may have been applied to these prints. Ukiyo-e woodblock prints originate from the Japanese Tokugawa shogunate, also referred to as the Edo period, lasting from 1603 to 1868. While ukiyo-e prints started off as simplistic black and white prints, all the prints being examined here are nikashie, or full color prints created with multiple woodblock prints, one for each color. All of these prints are printed on Japanese paper, and a variety of pigments are used, ranging from organic, inorganic, some unique to Japanese art, whilst others are ubiquitous. I have a particular interest in this research in entan, or red lead. So red lead, or PB304, is an inorganic lead-based pigment that has been used since the 5th century BCE. It's one of the first synthetic pigments commonly used because while it can be found in small amounts naturally, it can also be easily synthesized by roasting white lead for an extended period of time. While red lead today is defined as PB304, historically it also had major impurities in the form of lead monoxide, either in its orthombic or tetragonal form, as the pigments massicot and litharge respectively. In this diagram, you can see how these impurities are introduced into the red lead, either by under-roasting or over-roasting the pigment. An example of this was found in unused samples of red lead dating from the 8th century in a Japanese tomb, where it was found that samples labeled as entan were in fact only 6 to 26% red lead, with the remainder being lead monoxide. Red lead is a little less common in Western art, oftentimes appearing in murals or pottery, but it does make a common appearance in Asian art as a pigment in prints, paintings, and murals. After the introduction of synthetic pigments into Japan, red lead was one of the first pigments to leave the ukiyo-e palette, likely due to its tendency to blacken. In English, most of the research done into red lead is exclusively done in the context of murals and pottery. So, lead-based pigments are known to discolor. Infamously, in Western art, white lead is known to turn gray and blacken over time. Red lead is also observed to similarly change color, and this discoloration can change from brown to black to a metallic silver color. This is believed to be the formation of potentially two different products, either the formation of platinoite through the exposure to dilute sulfuric acid by way of atmospheric pollutants, or through the formation of lead sulfide through the exposure to hydrogen sulfide. This is the same reaction that causes the discoloration of white lead, but in red lead, it's known to take place at a much slower rate. The reason for this discoloration is particularly interesting on Japanese prints for two reasons. Number one, particular patterns are observed in the discoloration, and number two, there's some suspicion that some amount of this discoloration may be intentionally applied onto prints. So the patterns observed are these, either lines streaking across the print like this, or a sort of haloing effect, where around the edges of the printed area, there's this section of undiscolored pigment along the edges. The reasons for these patterns as of right now are completely unknown. Regarding intentionality, there was a study carried out by Walsh et al. That suggests that certain areas of discoloration were intentionally applied. It's also possible that artists intentionally used red lead knowing that it would darken, as even modern sources describing the pigment note that it turns black or browns within several years. Intentionality is very important to consider, as it can affect how prints are considered as a whole and potential treatment plans for extremely darkened prints. So there were essentially two parts to my research. I did the examination of extant and discolored works in the collection of the Rijksmuseum, and also I created, aged, and examined reconstructed prints that I made. And of course, there was some level of comparison between these two. Prints from the Rijksmuseum were chosen based on the amount of immediately visible discoloration in order to choose a large range of years. The range of years I ended up examining was 89, and the total, I just looked at 9 prints in total, and here's some examples. This is the earliest print I looked at. This is an example of one of the more heavily discolored prints I looked at, and this was the latest print I looked at. So, first, I worked with Leila Savage and performed macro X-ray fluorescence on each of the prints to determine if there was indeed red lead in all these suspected areas, and if other elements of interest, such as sulfur, were also apparent in significant amounts. And then from there, I attempted to find an analytical method that could identify the source of the discoloration. First, I worked with Luc Meijans to test out X-ray diffraction. X-ray diffraction, and I also worked with Inez van der Werf to test out Raman spectroscopy. Sadly, both these methods did not identify the discoloration. And then finally, I also carried out microscopy myself on both the examined prints, on the Rijksmuseum's prints and the reconstructed samples I made. The way I made my reconstruction instructions was a bit complicated. After some reading, I realized that there's little to no sources that survive today on how these prints were originally made, and what sources we have today are based on current craft tradition rather than historic sources. So because of this, I had to look at a lot of modern sources, compare them, and do a lot of testing to create a composite recipe. While creating this reconstruction, I determined that there were 3 variables that I found really affected the printing process and I wanted to examine further. And these were the thickness of the paper, the amount of impurities in the pigment, which was lead monoxide added by me intentionally, and how finely ground the pigment was. For these variables, I created pigment mixtures of pure red lead, pure lead monoxide, and a 50-50 mixture of the two to test the effects of impurities. For the grind, I took the pigment as it was apparent from the manufacturer, and then I also created a second set that I ground further. And then for the paper, I simply examined the prints I looked at from the Rijksmuseum and found the thickest and thinnest papers apparent and found comparative in the collection of the Rijksmuseum. Next, I'm going to show you a video of me producing some of these prints, but before that, there were some steps that took place before the video. First of all, this is the wood block that I ended up carving myself. It's made out of cherry wood. The shape and design is completely arbitrary, just to get a wide variety of shapes to see if anything induced discoloration differently. And before the video starts, I also sized and humidified all the papers used myself. So this is the video. Hopefully it plays. Yes, okay. So here you can see me taking the binding agent, which is rice starch paste, and applying it directly to the woodblock. And then I come over here with the brush, and this is the pigment, in this case just pure red lead, and it's mixed with a small amount of water already. And I take the brush, and I mix the pigment and water together quite thoroughly on the brush until I feel like I've picked up most of it and it's combined thoroughly. And then I'm going to apply that brush directly onto the block. This takes a little bit. Sorry about that. Yeah, and you mix the binding agent and the pigment directly on the block. From there, you mix it in circular motions to make sure that it's as even as possible, and you just really mix it together to make sure that there's no large pools of pigment. Once that's done, you take the paper. I forgot how long this is. Okay. I was very thorough when making these. Yeah. Now you take my pre-humidified and pre-sized pieces of paper that are sitting here, and you take it and you line it up in the registration marks that I've carved in the corner of the block. You place it down, and then I'm going to use a very complicated tool for the rubbing, which is a tablespoon, recommended to me by a local Dutch printer. And I'm not going to show you the very end product because I rub for approximately 2 minutes straight. But you end up with a print that looks like this. Okay. Once I had the reconstructions done, I had to artificially age the samples. I did a lot of reading and decided to test out a method originally designed for the tarnishing of metals by the Canadian Conservation Institute. I boiled chicken eggs, and while they were still warm, I peeled them and placed them in a sealed container with the samples. This worked fantastically, and after 3 hours, the samples were no longer discoloring to the naked eye. I also attempted intentional patination, following the method proposed by Finlayson et al., where she essentially suggested that if you printed acetic acid over the prints prior to exposing them to a source of hydrogen sulfide, it would create a more even and silvery discoloration, and this was hugely successful. The acetic acid prints were much more silvery and had a much more even discoloration than those only exposed to the eggs. While printing the reconstruction, I found that the thickness of the paper did not have an effect on the quality of the print, and in fact did not have significance on any part of the printing, and I will not be mentioning it further. In contrast, the ratio of red lead to lead monoxide was hugely significant and affected every element of the print. Generally, the more red lead that was in a sample, the easier it was to produce an even and consistent print with no lines left behind by the printing brush. In contrast, lead monoxide was very difficult to print with. It did not mix well with water or paste and often printed very thinly and in clumps, no matter how much it was manipulated. Here you can see that there's like a decreasing amount of coverage as the amount of red lead decreases and the amount of lead monoxide increases. During the aging of the prints, it was also found that as the more lead monoxide was added, the darker the discoloration became. It was also found that this discoloration was much more likely to become silvery and metallic the more lead monoxide was added. I should note that there's no evidence the Japanese printmakers used lead monoxide as a pigment, but the quality of the final print produced and how much it discolored may have been affected by how much lead monoxide was apparent as an impurity. It was also found that the grind of the pigment was significant during the printing process because over-grinding the pigment actually made it hydrophobic and very difficult to mix with water. and I had to work the pigment a lot more in order to get a print that was of quality enough for me to use for the research. During aging, I found the reason for the streaks that were apparent, it was a byproduct of the printing process. On prints that were initially printed very even with very few clumps and streaks, discoloration was generally very even. When printing with a brush such as you use here with very stiff bristles, it's very easy to leave behind streaks on the paper that become more apparent when the contrast between the pigment and the paper increases after discoloration, as you can see here. The other pattern observed in the Rijksmuseum prints, the haloing, was not replicated, and as a result, I could not conclude why it was produced. When examining the reconstructed samples under magnification, several things became immediately apparent. The ratio of red lead to lead monoxide seemed particularly significant to how the samples appeared, and the grind of the pigment affected the appearance of the samples, but not nearly as much. It can generally be said that red lead created a uniform layer across the print, which entirely covered the porous surface, but as more lead monoxide was added, the layer became thinner and more uneven. When comparing the Rijksmuseum's prints to my reconstructed prints under the microscope, it was found that the non-discolored areas of the prints most resembled reconstructed prints printed with the pigment mixture rather than the pure red lead, and both samples were found to have incomplete coverage with paper fibers still visible and had pigment particles of varying sizes. So this is an example of one of my reconstructed samples, and this is a micrograph of one of the Rijksmuseum prints, and I find them to be quite similar. For the analysis of the prints using macro XRF, it was found that red lead was apparent in all of the suspected areas of each print. Woo. In particular, red lead was found more commonly in architectural features, though it was also found in clothing, accessories, and landscapes. Sulfur was not detected in any of these areas, but this is likely a limitation of the analytical process. It was observed that a sulfur-containing pigment, orpiment, was apparent on 5 of the 9 prints examined, though it could not be determined if this had any effect on whether or not these prints discolored more or less. As stated previously, when tested, both X-ray diffraction and Raman spectroscopy were able to identify the existence of red lead, but were not able to identify the identity of the discoloration, likely due to the thinness of the layer apparent and its amorphous nature. While it was disappointing that these methods did not work, all was not lost. Shortly after I finished my thesis, I got a chance to have Zane's and micro-XRD analysis performed by Marine Cote and Clement Hall at the European Synchrotron Radiation Facility. Zane's was very elucidating. I was able to find that all samples, including those with no pigment, had a peak at the sulfate marker, so here, indicating that any detected sulfate originated from the paper rather than lead products. A sulfide peak only developed after aging, as you can see here, indicating that a sulfide peak only developed after aging, indicating that the source of the discoloration is likely due to a sulfide product, likely lead sulfide. And it should also be noted that this sulfate peak, even after aging, was found to be unchanged. Specifically, it was found that prior to aging, there was very little sulfide compared to sulfate, and after aging, this ratio increased significantly. In particular, in the pure lead monoxide samples, this increase was observed the most, which is logical considering that during the printing process, it was found that the more lead monoxide was added to a sample, the darker and more discolored the samples became. So these graphs essentially chart out the ratio of sulfide to sulfate. And here you can see that these are all the samples with pigment on them. And you can see that these are unaged or have no pigment. And once you age it, the amount of sulfide jumps up. This graph is essentially a zoom in of this portion of the graph and is illustrating that while the samples with red lead do have an increase in sulfide, the samples with pure lead monoxide have a much greater increase in lead sulfide after aging. Unfortunately, it was found that the micro XRD analysis did not prove any more effective than other XRD analysis, likely showing that the black, silver, and gray products formed are amorphous and cannot be detected using this method at all. Here's a graph showing that the two most likely products have little to no correlation with what I detected. So some quick conclusions. I found that one of the patterns observed in the discolorations that I observed at the very beginning was in fact probably a byproduct of the printing process, while the other one observed, the haloing, could not be recreated and the cause could not be determined. I found that the thickness of the paper did not affect the printing process or discoloration of the prints, at least at this scale. The grind of the pigments significantly affected the printing process, with too much grinding making the pigments hydrophobic and potentially causing printing errors. The ratio of pigments was by far the most important element, with increasing amounts of impurities causing less consistent prints, prints that discolored more rapidly, more completely, and more readily turned to silver. Intentional discoloration was found to be very easy to induce, though it could not be proven that it was performed. XRD and Raman spectroscopy were not effective in identifying the degradation products, but Zane's was, showing that a sulfide species was developing after aging, at least in my reconstructed samples, indicating that lead sulfide is likely the form of the discoloration. So some quick points of further research. First, transmission electron microscopy might be another way to identify particles of lead sulfide that cannot be detected with XRD on my reconstructed samples, and this can be used to further confirm the results of my Zane's analysis. And now that I've determined that it seems that the ratio of red lead to impurities significantly affects the amount that it discolors and the final color of the discoloration, I think the next step would be to determine the actual ratio of red lead on historical prints. This could help to identify prints that are at a higher risk for discoloration and to generally determine the quality of artist pigments used at the time. Another interesting point is the actual source of the haloing pattern observed. Further testing is needed to determine what is happening. I have two hypotheses. It could be a diffusion limited reaction causing some sort of pattern similar to the one seen here on this silver gelatin print, silver gelatin glass plate. Or it could be some sort of reaction taking place with the black sumi ink that surrounds all areas of printing. Further testing is needed. Finally, there is one last point that I have not mentioned up to this point, but is very interesting. On some of the prints observed during the macro XRF analysis, there was a noted border. It was noted that around areas of red lead that there was this border of potassium detected. I have no clue where this comes from. I do not know if it comes from the detector. I do not know if it's a technique. I have no clue. Further research is needed. I would like to thank these people for all their help in making this research possible. Here are my sources. And if you want to know more, here's a link to my thesis and a link to a copy of this presentation.